Welcome to today's Explainer, everyone. Think of this as your definitive, deep dive lecture into one of the most absolutely crucial topics in software engineering, safety requirements. We're going to be walking through section 12.2 from our core text today. Now, setting a professional but focused tone is really important right out of the gate here, because the concepts we are going to unpack don't just dictate how we write a program, they quite literally dictate how we protect human lives. Before we dive into the deep end, it really helps to understand a foundational concept, and that is a system state. A system state is, simply put, the specific condition or mode that a system is operating in at any given moment. You can think of an airplane being in flight mode versus ground mode. Our ultimate job as engineers is to make sure our systems never, ever enter a highly dangerous state. So let's jump right in.
Here is our roadmap for today. We'll start with Section 1, Introduction to Safety Requirements. Then Section 2, Stage 1, Hazard Identification. Section 3, Stage 2, Hazard Assessment. Section 4, Stage 3, Hazard Analysis. Section 5 covers Stage 4, Risk Reduction. And finally, Section 6 will be our summary and exam focus.
All right, Section 1, Introduction to Safety Requirements. To truly wrap our heads around why this matters so much, we have to look beyond the code itself.
Let's start with a stark, real-world tragedy to highlight our core problem. Picture this. It's 1993, and an aircraft is attempting to land at Warsaw Airport in a really severe thunderstorm. For 9 agonizing seconds after touching down on the tarmac, the computer-controlled braking system just did not work. The plane ended up running off the runway, which led to a fatal crash. But here's the really chilling part for us as engineers. The software behavior exactly matched its specification. There were absolutely no bugs in the code. Zero. The system was meticulously designed to prevent reverse thrust while the plane was in the air, which obviously is a critical safety measure. You don't want reverse thrust mid-flight. However, the specification completely failed to account for a rare landing scenario. You see, the plane was on the ground, but it was aquaplaning. The tires were essentially skimming on a layer of water, so they weren't spinning. And because those wheels weren't rotating, the sensors falsely reported to the computer that the plane was still flying. The software worked perfectly according to its instructions, but the system as a whole failed catastrophically. What this proves, without a doubt, is that perfectly engineered code simply isn't enough if your specification does not match reality. Because of tragedies exactly like Warsaw, safety requirements focus heavily on protection. Now, most of the time, software engineers love building features, right? We write functional requirements that tell a system what it shall do, but safety requirements are totally different. They are uniquely framed as shall not statements. They explicitly define unacceptable system behavior. We are specifying what the system absolutely must never do in order to maintain a safe state. So to quickly recap our introduction, functional requirements tell the system what to do, while safety requirements dictate what the system must never do to prevent accidents. With that foundation set, let's move forward.
That brings us to Section 2, Stage 1, Hazard Identification. So how do we actually figure out what our shall not statements need to be? Well, we use a hazard-driven specification process. This is the overarching framework that engineers use to manage risk. It's broken down into 4 distinct steps: identifying the hazards, assessing them, analyzing their root causes, and finally, reducing the risk. Keep in mind, this is a continuous iterative life cycle. It's not just a one-off checklist where you do step 1 and never look back. You might be analyzing a risk in stage 3, discover a brand new hazard, and have to cycle right back to stage 1. This process is our clear roadmap for the rest of this explainer.
Before we go any further, let's pause and explicitly define our terms, because students mix this up all the time. A hazard is a condition with the potential for causing or contributing to an accident. It is crucially important to understand that a hazard is not the accident itself. Think of it like a puddle of oil on a factory floor. The puddle is the hazard. Someone slipping on that puddle and breaking their arm, that is the accident. In software engineering, we want to identify the puddles before anyone slips.
Let's brainstorm some possible hazards together using a classic textbook example, an automated insulin pump attached to a patient. What could possibly go wrong here? Well, we have physical hazards, like the machine just physically breaking or cracking, electrical hazards, like interference from a nearby MRI machine scrambling the circuits, biological hazards, such as the patient having a severe allergic reaction to the medical adhesive, and of course, software hazards, like computing an incorrect insulin dose.
Notice that software-related hazards almost always involve a failure to deliver a critical service or a failure to properly monitor the system. Administering a massive overdose or a dangerous underdose are direct results of these software hazards. To summarize, Stage 1, our main goal here is to aggressively brainstorm and list out every conceivable hazard, from hardware wear and tear to software computation errors that could threaten the system.
Moving right along to Section 3, Stage 2, Hazard Assessment. Once we've brainstormed and identified dozens, maybe hundreds of these hazards, we have to assess and prioritize them. We simply cannot treat every single hazard with the exact same level of urgency.
To prioritize these hazards, engineers use something called the risk triangle. As you look at this model, you'll see risks are categorized into 3 distinct levels of acceptability based on 2 key factors: how probable they are to occur and how severe the damage would be if they actually did. At the very top, we have the unacceptable region. These are catastrophic risks that threaten human life and absolutely cannot be tolerated under any circumstances. Down at the bottom, we have the acceptable region. These are negligible risks where the consequences are minor and highly unlikely. And right there in the middle, we have a very special zone called ALRP.
ALARP stands for as low as reasonably practical. This is an absolutely crucial principle in engineering, and I promise you it's heavily tested in exams. It means the system should be designed so that these risks are minimized as much as possible, but subject to realistic costs and delivery constraints. Why is this so important? Because software engineering is bound by real-world economics. If we decided to spend $1 billion engineering a flawless, triple-redundant hardware monitor for a very minor risk on our insulin pump, literally nobody would be able to afford the pump. Delaying a project for years or making life-saving technology unaffordable also costs lives. So for an ALARP risk, like a temporary hardware monitor glitch that causes a brief underdose before the user notices, we minimize it for sure, but we balance the engineering effort against reality.
When we map all these concepts out systematically, we get a risk classification table, much like this one for our insulin pump. Check out the top row. An insulin overdose computation has a medium probability, but a very high accident severity. That makes the estimated risk high, and therefore completely intolerable. We have to fix that. Now compare that to the bottom row. An allergic reaction is low probability and low severity, so it is simply acceptable. We note it, but we don't completely redesign the software around it. And right in the middle, that hardware monitoring failure is classified as ALRP. A table like this is how engineers systematically prioritize their focus. So, to recap Stage 2, we take all those identified hazards and assess them using the risk triangle to decide whether they are intolerable, acceptable, or ALRP. This tells us exactly where we need to spend our engineering resources. All right, Section 4, Stage 3, Hazard Analysis. Now that we know exactly which risks are intolerable or ALRP, we have to discover their root causes so we can actually prevent them.
There are basically 2 ways to do root cause analysis. Top-down is a deductive method. You start with the big hazard and work backwards to find the specific system failures that caused it. Bottom-up, on the other hand, is an inductive method. You start by proposing a random component failure and work forwards to see what hazards might eventually result from it. In software engineering, top-down is vastly superior and way more commonly used. Why? Well, because modern software has billions of possible internal component states. It is nearly impossible to look at every single line of code from the bottom up and guess which random bit flip might eventually cause a hazard. It is so much easier to start with the hazard itself and deduce backwards.
The most famous top-down method is called fault tree analysis. I want you to make sure you have this definition memorized. It is a deductive technique that works backwards from a hazard to discover its root causes. Let's look at how we actually apply this step by step. The mechanics of analyzing a fault tree are actually quite logical. It's like a giant puzzle. You place the hazard, let's say incorrect insulin dose, at the very top, the root of the tree. Then you work backwards using logic gates. You ask, could this overdose be caused by a software computation error or a hardware sensor error? If it's a sensor error, does it require sensor A and sensor B to fail simultaneously to actually trigger the overdose? You just trace these branches all the way down, breaking the problem apart until you identify every single foundational hardware or software failure that could trigger that main hazard. To summarize, Stage 3, we select our intolerable and ALARP hazards, place them at the top of a fault tree, and deduce downwards to map out every single root cause that we need to address in our code. Section 5, Stage 4. Risk reduction. With all of those root causes clearly mapped out at the bottom of our fault tree, we can finally figure out how to fix or mitigate them.
There are 3 overarching strategies engineers use to reduce risk once it is identified. First, hazard avoidance. This means designing the system so the hazard is physically or logically impossible. For example, building a two-handed operation switch on a heavy mechanical press so the operator cannot physically have their hand under the blade when it drops. Second, hazard detection and removal. This means designing the system to detect the hazard and neutralize it before an accident happens, kind of like a chemical plant software program that detects high pressure and automatically opens a relief valve. And third, damage limitation. This is accepting that the accident might happen, but designing the system to minimize the damage if it does. Think of deploying a parachute for a delivery drone if its motors suddenly fail. The crash still happens, but it falls slowly, drastically limiting the damage to people down below.
So how does this actually look in practice for a software engineer? Let's say our fault tree revealed that a floating point arithmetic error in the program could cause a massive insulin overdose. We apply a risk reduction strategy to translate that directly into a concrete executable software requirement. For example, System Requirement 4. The system shall include an exception handler for all arithmetic errors and shut down safely. We detected the root cause, and we wrote a strict requirement to ensure a safe shutdown state. To recap Stage 4, we take the root causes identified in our fault tree and we write strict, executable software requirements using avoidance, detection, or damage limitation to ensure the hazard is neutralized.
All right, Section 6, Summary and Exam Focus. We've covered a lot of ground today, going step by step through a really vital engineering process. So let's transition into a strict recap of the core ideas. Listen up, because this is exactly what you need to know for your test.
Grab your pens, write these down. First, you absolutely must be able to list the 4 stages of hazard-driven specification in order: identification, assessment, analysis, and risk reduction. Second, you must be able to define the ALARP principle, as low as reasonably practical, and explain how it balances risk minimization against the very real economic realities of building software. And third, you need to be able to explain how a top-down fault tree works, placing the hazard at the top and deducting the root causes downwards using logic gates. Mastering this hazard-driven methodology perfectly bridges into our next topic, where we'll look at broader safety engineering processes.
I want to leave you with a final, slightly provocative thought. The ultimate challenge in software engineering isn't just writing elegant code. It's finding the balance. Overprotecting a system with endless redundancies makes it too complex and too expensive to ever actually build, meaning life-saving tools never reach the public. But underprotecting it, well, that costs lives. Where will you draw the line in your next program? Thanks for joining me on this explainer, and I'll see you all in the next session.